Hi, thanks for coming. In the next 15 minutes, I will present breaking parser logic, take your path normalization of and path 0 days out. Although path traversal is a common problem in web applications, but it's still hard to apply the good security mechanism. There are lots of pitfalls and edge cases that programmers may ignore. But the only thing they care about is still // In this talk, we try to pay more attention on analyzing parser logic and path normalizations. During this process, we noticed an interesting feature that could be perfectly applied on multi-layered architecture. We will detail this attack surface and give several case studies. Okay, let's go. Hi, I'm Orange, a security researcher from DevCore. We provide the most professional rating service and penetration testing in Asia. My job is researching and finding new 0 days and attack surface. I'm also the member of HackCon. We hold the largest hacker conference in Taiwan. Apart from that, I'm also a speaker, bounty hunter, and CTF player. This is our agenda today. We will first highlight the blind side on path normalization and talk about why I focus on this. By knowing the blind side, we try to review existing web frameworks and find bugs from them. We will show 0 days on both Ruby on Rails and Spring Framework. Lastly, the new attack surface. Of course, in order to convince this is awesome, we will give several bug bounty cases. Okay, first, let's learn a new word, normalize. To make standard, determine the value by comparison to an item of non-standard value. The definition is easy, but if every system has their own standards, it must be problems. And the next, why normalization? In security, it means that you need to protect something. In order to fix a bug without impacting business logic, it's common to apply a workaround or a filter instead of patching the bug directly. To apply the filter, you need to pass the data first, but it's hard to implement a well-designed parser. Everyone follows RFC as their standard. RFC defined the specification, but didn't tell you how to implement. So the more complicated the data format is, the harder it is to pass. So what's wrong with the normalization? Yes, inconsistency. This is a typical dangerous pattern and easy to find problems on it. The behavior in check must be the same as the behavior in use. Otherwise, the check function will be bypassed. It's just like my SSIF talk in Black Hat last year. Finding inconsistency between URL parsers and URL fetchers that leads to whole SSIF bypass. So for the past 2 years, I pay more attention on the bug inconsistency. For example, this is an interesting implementation in Java. There are different file handlers for each operating system. In Windows, Java treats the file as UNC path, but Linux treats it as URL. The most difference between each other is the URL supports query string, but UNC doesn't. Once we know that, there are several dangerous patterns. For example, the method getPath only returns the path before the question mark, but the file system still recognizes O as its path. So here is an inconsistency. On the other hand, the method getFile or to external from return O, the URL path. But if the check relies on the normalization result from them, we can forge a valid path to bypass the check and read arbitrary file on the Linux. So back to our topic, why I target path normalization? Because most websites handle files. Also, path traversal is an old problem in many web applications, but that is also the path with lots of protections and bypasses. As I mentioned before, there are lots of dangerous patterns, so that if you can find the difference between the check and the use, you can bypass the protection. Another reason is, in large projects, the code changes too fast and lack an overall security review. For the new commit, is there any side effect or bypass existing security mechanism? Who knows? Let's talk about Mojara. Java Server Faces. Java Server Faces is a standard on the Java EE, but it's just a standard needs someone to implement. So the top two implementations in the world are the MyFaces by Apache and the Mojara by Oracle. While reading advisories, I noticed the report that reviewed Mojara and find CVE 2013-3827. The report also inspired me to dig more into the source. With a couple of days, I find a new vulnerability. It's a very obvious path traversal. Just read the file from query string. While I find this, I was very curious about why the advisory didn't notice that. With a little bit investigation, I find the reason. The bug was committed in 2015, but the code review was done in 2013. This points out a serious problem. Mojara is a very fundamental library, but since there is no one do a formal security review since 2015. So that's the reason to push me dig into the path normalization on web frameworks and applications. So let's start our topic. First, how parsers could be failed. Here is a very obvious programming error. Can you spot the bug? This code was copied from Grails. Grails is a powerful Groovy-based web application framework. If you want to use Groovy as your backend language, you must have heard about Grails. And this is the part of static file handling. The argument relative path is attacker controllable. In order to be compatible with Windows environment, the code replaces current file separator with /. So, have you found the bug? Okay, the answer is the method replace. Grails would like to replace current file separator with regular expression. So Grails escaped the path by pattern.quote. But was the replace used correctly? This is the prototype of method replace. But in Java, replace has a big brother, and his name is replaceAll. Both methods are very similar, but the only difference between each other is the meaning of the first argument. The first argument in replace is the literal string to be replaced, but the other is the regular expression to be executed. Both arguments are the string type. It seems the developer used the wrong method. The pattern.quote encloses the current file separator with escape Q and escape E. Because of the misuse, Grails will recognize the escape regular expression as literal string. As the result, there is a new / in the Grails. Yes, fails everywhere. Even worse, the buggy code was committed in 2014, so the bug has been there for several years. The next topic is how single slash could be failed. Maybe you have set out several paths in the past, but does your path end with a slash? This is a good question. Is it important? Yes, let me show you how single slash could be failed. This is an off by slash fail on Nginx. The first time this problem be shown was in the end of 2016, and this credit to Atlas. Although this is not new, but it's still worth to mention, this is a good attack vector without too much people known, and the idea appears in real world again and again. In Nginx, there is an alias directive, and it can define a replacement for the specified location. This directive is very common in web architectures. In practical applications such as Django and Rails are not familiar with handling static files. So it's prevalent pattern to put the Nginx in front of them. But due to the lack of churn slash in the location rule, the slash static ... will also hit the alias block. So as the result, Nginx will append the remaining part to the home app static, and we can traverse one label to parent directory. So how single slash could be failed? You can search how to serve static file with Nginx on Google or Stack Overflow, and you will find numerous answers with mistakes. This problem is also common in the implementation that you need to process the path by yourself. It's just like string copying in C language. To append a slash or not is a serious problem to you. So how to find this problem in real world? We give a private bug bounty case here. From direct accessing the access folder, Nginx returned 403 forbidden. However, when we try the slash access ... it also returned 403. It looks like we have successfully traversed a label to parent directory. But how to prove this? We append access/app.js again and check the content. Yes, the same. So now we can download all the source and configuration file on the web root. In this case, we got several sensitive data, such as the Django secret key and the SQLite database. So for the past several months, I start to review the path normalization and parser part on web applications. Of course, we find several problems in diverse implementation. Here is the list. So the next section is in-depth review of existing implementations. Due to the time consideration and our new finding is more important, we will only show you two cases. The first one, directory traversal on Spring framework. We all agree that Spring is the famous framework in Java web ecosystem. So we start from the patch of CVE 2014-3625. It's also a path traversal. In order to prevent similar bug again, Spring applied several security mechanisms. From the method name, we know Spring first checked whether the path is valid or not, and used its resource on the location as the last guardian to ensure the path on the appropriate locations. This is the simplified version of method is invalid path. It's just a simple blacklist. And the most important is, if there is any dot in the path, Spring will normalize the path, check, and return a boolean. As I mentioned before, this is a dangerous pattern. Spring just relies on this boolean to protect all the system. So if you find a problem in the clean path or inconsistency between the check and the use, you can bypass all the protection. So how clean path work? This is the source code of clean path. In order to be compatible with Windows environment, it simply replaces / to /. Spring also separates the path with the /, check the element one by one, and store the result into path element. If the element is a single dot, Spring just do nothing. But if it is the parent directory, Spring will set a flag to remove the item in next iteration. In the end, Spring used the forward slash to join all the elements. Okay, that's all. Did you find the problem? The problem is Spring allows the empty element. That means you can forge an empty element in path array. During the normalization, it will be normalized with the parent directory and cause the inconsistency with file system. It seems to be a small problem, but the impact is huge. This table shows the difference between the clean path and the file system. Due to the empty element, when there is more than one slash in the path, things start going wrong. The method is invalid path return true because there is no dot dot in the result. So Spring believes without any dot and read the file with user supplied path. So how to export it? We clone the Spring official sample from GitHub. As you can see the payload, there are 6 slash, normalize the next 6 dot dot slash. This exploit also works on the container such as Tomcat. As a secured container, Tomcat by default enables several security features. But this exploit perfectly bypasses all restrictions. As a result, we can read arbitrary file on Windows. So how to fix? Do not use Windows. Yeah, this is the real mitigation from Spring official website. Excellent. As a bonus, let's talk about the code infectivity. Programmers follow the dry principle. Don't repeat yourself. And Spring is a popular framework under a free software license, so lots of projects refer the code from Spring. Spark is also a famous framework for web applications. In 2014, Spark wanted to improve their security mechanism on static file handling. But since writing a good parser is very hard, so it just copied the code from Spring. As the result, Spark also copied a similar problem into their code base, so Spark also suffered from this vulnerability. The next case is Ruby on Rails. Sprocket is the asset pipeline system in Rails, which means all static files will be managed, compiled, and served by Sprocket. And of course, we find a problem here. But unfortunately, Rails only uses the asset pipeline system on development mode. Although this only affects development servers, the default Rails command is on the thread. So you can simply reproduce the bug by just 2 commands, Rails new and Rails server. Due to the time consideration, I will not go into too much detail. The root cause is that Sprocket supports an undocumented file scheme in the past. There are several pieces in this exploit, but because of the time, you can check the detail after this talk. We will just go to the next page. But it is still worth to say this is possible for code execution. Because of the support of file scheme, you can override some internal options with your query string. As an asset pipeline system, Sprocket will compile the content while processing the file. If the file extension is ERB, Sprocket will interpret the file as Ruby template engine. This feature could be combined with file upload attack. You upload a malicious file to temp folder and execute the code by Sprocket. Are you okay? The boring part is over. You can stretch yourself a little bit. Okay, here's the cat, and let's go to the most interesting part. While I was reading the advisory, While I was reading the source, I noticed a feature that could be perfectly exploited on multi-layered architectures. In the following page, I will introduce the idea and several cases, including an access control bypass in Uber and 2 remote code executions. In addition, I would like to thank Emerson and Binder for the open-minded vulnerability disclosure and their quick response time. It's a very good experience working with them. We start with the HTTP feature, URL path parameter. It can define information for the specified path segment. Some researchers have already pointed out this feature may lead to security issues, but their concern still depend on programming files. When I saw this, I was thinking about how to make this feature more severely. Yes, I find reverse proxy. Reverse proxy is a common web architecture. There are several benefits: resource sharing, load balance, cache, and security. For example, you can share different services on the same port or IP address, or use load balance to distribute the request to different backend servers. As the security, reverse proxy can isolate the server from outside and configure the access control in proxy path. This is a classic reverse proxy architecture. As I said before, it's a prevalent pattern to serve static file directly and pass the business logic to backend service. I have talked about the off// problem, but now we focus on the interaction between the proxy and backend servers. Nginx will serve it directly if the incoming request match the static pattern, such as files and scripts. But if it is the request for business logic, Nginx will pass to backend servers. Okay, back to our topic. So what will happen when the feature makes the reverse proxy? URL path parameter is defined in HTTP specification, but not all web servers care about it. However, Java mostly supports this feature. Reverse proxy is not a single request, single server handling architecture. The same request will be interpreted by different web servers. So the inconsistency between the proxy and backend servers will lead to security problems. It seems popular to give a name for vulnerability, so I named this bad proxy. Okay, not really, just kidding. The domain is still available for buy. So how dangerous this could be? In the reverse proxy, it can bypass access control, no matter it's blacklist or whitelist. It can also escape from current context mapping to access the management interface and other contexts on the same server. The apps always believe that no one can touch their internal service. But today, this is exposed to outside, and they must be lots of fun for hackers. And I affect by this. This is the architecture's problem and vulnerable by default without any programming errors. So if you are using reverse proxy with Java as your backend service, you are under threat. Basically, this is a huge attack surface. Think about how many reverse proxy in the world could be bypassed so that you can touch many internal services from outside. For an easy example to understand, Tomcat exposed the application portal in localhost and maps to outside by a patch. Due to the normalization of a patch, we cannot direct access the backend management interface. However, we can use our traversal check .. to traverse one label to touch the root of Tomcat. A patch first handles this request. From the view of a patch, .. is the normal folder name and match the context mapping, so it passes to backend service. But in Tomcat, .. is the parent directory and will normalize with the portal. As a result, we can access all applications on the Tomcat, including the management interface. Everything looks good from their side, but when they put all together, everything starts going wrong. Okay, by knowing the theory, let's see real-world cases. The first case is Uber. Uber disallowed direct access to the domain uberinternal.com. From the name, we know this is the domain for internal purpose. Once we access, it redirects us to the one login single sign-on service, and this redirection was done by Nginx. We find the domain jira.uberinternal.com, and we also know that Jira is a Java-based application. It seems to be reverse processing again. With a little bit searching, we find this website exposes a status API, and this appears to be the whitelist for monitor purpose. We applied our traversal trick again. It looks good in Nginx and match the whitelist prefix, so pass to Jira. As the result, we can access the Jira dashboard and see the internal project. And this is another portal we accessed, an internal code review portal. Okay, so next, what can we do if we bypass the access control? We will give a code execution case in Binder. Basically, I find this code execution in another bounty program. Also, I got a code execution. I find my target is not in their bounty scope because it's on a third-party service. But fortunately, there is also a bounty program in that service provider. So in the following case, I will use their site as an example. This is the screenshot for the website. It's just a login page without too much functionality. When I would like to hack something, the first thing I care about is the HTTP header. From the header, we can observe many interesting information. The header told you that it is running on the Nginx. However, the response also set a special cookie, JSession ID. It seems to be the default session name in Tomcat. But why Nginx need this cookie? From our experience, we believe this is also the reverse proxy architecture. By the way, this is also a good methodology to know whether the target is running on the reverse proxy or not. We applied our traversal trick and got a cool patch. This is a 404 patch, but the special is the patch was returned by Tomcat. This represents that we have already passed the first proxy and accessed the backend service. Another thing is, from the error message, we got an important hint. The hint is that our request path will be the path info in the backend index.cfn. From the hint, we can construct the server configuration in our mind. Nginx just rewrite the request to backend index.cfn. But for the // it will raise an 400 error because the path jumped out of the web root. However, our trick can pass through the proxy and normalize the index.cfn. So we can touch the root in Tomcat. As you've seen, the file extension is CFN, the Code Fusion knockout language. From the extension, we can guess what backend engine is it. In this case, it is running on the Relo, an open-source CFN engine. And from the Relo menu, we also know that the management interface is on the Relo context /admin/web.cfn. This is the screenshot for the management interface. But did you find something wrong? Yes, the interface just asks you to set a new password. But is that easy? No. The first time I saw it was not like this. It's a normal login page. However, when I refreshed several times, the page changed. So what's wrong with it? With a little bit investigation, I think I find the root cause. When there is a large number of requests, the website will use the cloud to scale up automatically. But while scaling up, it seems to forget to put the password file. So this is the root cause to invite you to enter the new password. However, not all instances are vulnerable. It seems to be only 3 to 4 misconfigurations. So we only have about 16% probability to see the new password page. Although that a successful login is still not easy because there is a CAPTCHA in login process. And to make things worse, every request to the cloud will be dispatched randomly to different backend servers. For example, if the server in displaying the CAPTCHA is different from the server in receiving the credential, it will raise a wrong CAPTCHA error. So it's just like playing the lottery. We need to keep the station and poke the same server on both CAPTCHA and login process. With hundreds of try and error, we finally get into the manager interface. Once we enter the interface, the next question is how to pop our shell. In Redis, there are several ways to pop our shell. But due to the request being dispatched to different servers, we need to minify our steps. Here, we choose log injection. Redis supports many features. One is the customized template file. So we modify the 404 page to exception.log. And then we need to inject our malicious code into exception.log. However, while exploring this, we face a problem. The log file is too large to be executed. But did you remember the website will scale up when there are lots of requests? So that we can use heavy requests to force the cloud launch a new instance and exploit on that instance. Okay, now every 404 page is our backdoor, and we got a shell back. The last is our Amazon case. While searching for targets, we find a spatial domain. From the name, it seems to be the collaboration system for internal purpose. And from the copyright, we know this system was built from an open source project, Nastio. Nastio is a content management system for business application. It's written in Java. In that time, I just want to improve my Java auditing skill, so I start review the code. During the code review, we find several tiny bugs can be chained together to gain code execution. We first looked at the access control in Nastio. While auditing the source, we find Nastio maps all URL to a spatial authentication filter, and the first bug is lying on that. From the filter, we know most pages require a valid session, but some entrances can bypass that, such as login.csp. But how did the filter retrieve the current page to compare it with? It retrieved the path from HTTP servlet request. So what's the problem? In order to handle URL path parameter, Nastio truncates the path by semicolon. As I mentioned before, the behavior in URL path parameter are various. Every web server has its own implementation. The Nastio's way may be safe in containers such as Wi-Fi and WebLogic, but now it runs under Tomcat. The difference between the Nastio and the Tomcat will lead to security problems. So due to the truncation, we can forge a request that matches the whitelist in access control, but reach the unauthorized area in Nastio. However, we still could not do anything. In fact, most pages return a null pointer exception because the servlet logic was unable to obtain a valid credential. But this still gives us a chance to knock the door. From the configuration file, we noticed that how the Nastio is based on Syn framework. I have reviewed Syn several years ago and find numerous hacker-friendly features. So for me, the next step is training the first bug to access the unauthorized Syn framework. So let's talk about the Syn feature. In order to control the browser, Syn framework introduces a series of HTTP parameters. Action method is one of them. It can invoke specific expression language from the query string. It seems dangerous. However, there are some preconditions before the invocation. The invoked expression language must be in a certain format and in a file on the context root. For example, there is a file named foo.xhtml, and you can invoke the util.escape by the following URL. The feature looks good. You cannot control any file on remote server, therefore you can't invoke any expression language. However, there is one more crazy feature. To make things worse, if the previous invocation returns a string, and the string looks like an expression language, Syn framework will invoke again. Yes, it's double evaluation. The first feature is harmless, but the double evaluation is very scary. With the crazy feature, if we can control the return value, we can execute actual EL. So we need to find a good gadget. This is very similar to the ROP, return-oriented programming in binary exploitation. We choose the file with the long name. Why we choose this? It is because the request.get parameter returns the string that we can control from URL. Also, the whole tag is supposed to assign a variable. We can still execute the partial tag. So by training with the first access control bypass, we can now execute arbitrary EL without any authentication. But it's still not over yet. We failed to pop our shell. Syn also knows that EL is risky, so there is a blacklist to block dangerous invocations. However, it's just a simple string matching, and we all know that blacklist is always a bad idea. So we simply use the array-like operator to avoid the bad pattern. So let's summarize our steps and train all together. We first find the path normalization bug to bypass the access control. While we can access the unauthorized Syn servlet, we use the feature and choose a good gadget so that we can control the return value. We also prepare our second stage payload in the URL and use array-like operator to bypass the blacklist. The last step is to write our shell code with Java Reflection API and wait for our shell back. So this is the overview for how to exploring. I will explain each part one by one in detail. First, the yellow highlight is the access control bypass. In order to bypass the whitelist, we choose login.jsp as our prefix. Nastio will scan all the request paths and truncate until the first semicolon. Due to the inconsistency between Nastio and the container, we can bypass the authentication and touch the create file.xhtml. We choose this file because it will be handled by Syn framework. Once we can touch the Syn servlet, we use the action method to invoke partial expression language in a known file. Here we choose the gadget on the file with a long name. So why we choose this? It's because the return value of the request.get parameter is a string, and we can control from URL. So we prepared our second stage payload in the query string directory named for popup. As the crazy feature, Syn framework will invoke the value as expression language again. In order to avoid bad pattern, we use array-like operator to bypass the break list. We also use Java Reflection API to get all methods from java.len.runtime. The element index 7 is the method getRuntime to return runtime object. And the index 15 is the method exec with a string type argument. Okay, the last thing is the shell command. Here we would like to pass a shell back, and we got a shell. Okay, so how to prevent this type of attack? This is hard to fix because the URL pass parameter is a normal feature and not a bug in each side. According to my experience in bug reporting, most vendors cannot patch the bug completely in the first time. Their patch is bypassable. So we mitigate from two aspects. One is to isolate your backend application, remove the management interface and other contexts from your Java container. And the second is to ensure the behavior between the proxy and backend servers. But it seems there is no directive to disable the feature, so I write a patch for that. You can check the hyperlink after this talk. Okay, summary. In this talk, we first show the blind side about the path parser and path normalization, including the inconsistency, misuse method, and the off-by-slash problem. Then we introduce a new attack surface on the reverse proxy architecture that can bypass access control and escape from the context mapping. The last, we show several case studies on not only web applications and bug bounty programs. Here is the reference. Okay, the last page. Here is my contact information. Please let me know if you have any further question or new findings. Also, we will release the whole story of our case study in my blog. You can follow my Twitter to know the latest post. This is the end of my presentation. Thank you for being here. Thanks.